Log on, tune in, find out. Another good idea from Cambridge.
Welcome to the second half of this morning session. And the first talk in the second half is by Mike Hay on the completeness study on the class of Lex pairs.
Thank you. Good morning, everyone. Special good morning to the organizers of this meeting. Thank you kindly for accepting my talk. I found Cambridge to be both beautiful and inspiring, so I feel privileged to be here. The title is Completeness Study on a Class of Lax Pairs, and let me be more specific about what I mean with that when the time comes. First, I'll start with an introduction. And a lax pair, in the most basic sense, is a pair of linear equations that are associated with a nonlinear equation. This is a very loose description, and there's a lot of different kinds of lax pair. The kind that I'm interested in is written here. These are the two linear problems that I'm talking about. To keep it simple, I should say it's discrete lax pairs, they're discrete linear problems, and they lead to partial difference equations. A shift in the L direction is just L times phi, and a shift in the M direction is M times phi. At this point, I also wanted to note that my preferred notation is to say a shift in the L direction is a phi bar, or bar on anything represents a shift in the L direction, and a hat on anything represents a shift in the M direction. These two linear equations are associated with a nonlinear equation through their compatibility condition. And the compatibility condition is very easy to understand. If I take a closer look at my basic plaquette for the quad graph, there's two ways I can get from phi to phi bar hat. One way I can go along the bottom first. Phi bar is L phi, and then I can put a hat on all that by multiplying by M bar. So I have one expression for phi bar hat. Alternatively, I can go up first. Phi hat is M phi, and then go across, put a bar on all of that, and I have two expressions for phi bar hat. And the compatibility condition is simply the case where I expect these two things to agree. There's my compatibility condition, L hat M is equal to M bar L. Now, to make a bit more sense of that, these gestures, I have to keep still. I'm interested in these linear problems where phi is a two-component vector. So L and M are 2 by 2 matrices. As motivation for why I might look at lax pairs, they're very important. You can get information about the solution to the nonlinear equation through a lax pair, which is a difficult thing to do. And also, any nonlinear equation that has a lax pair is known to be integrable. So what I'm doing in this study is taking a class of lax pairs and finding every nonlinear equation that I can associate with that entire class of lax pairs. And I know that all of those equations will be integrable. Now let's see this thing in action. Here's an example for the lattice modified KdV equation. You can see inside the lax pair now, here the lax matrices L and M, and inside there we have X, which is the dependent variable which will solve the nonlinear equation. We have some arbitrary functions, lambda and mu, which are arbitrary functions of just one lattice direction. These are like parameters, but it's a non-autonomous system, so they're functions of one of the lattice directions. And we also have the spectral parameter nu. At the moment, it kind of seems to just cancel out, but in the second half of the talk, the spectral parameter nu will be vital. So we associate L and M with the LM KdV equation through the compatibility condition. Let's look at the 1-1 entry. I even put boxes on these things. I know you know how to multiply matrices, but I want the people who are not familiar with this tune to be able to sing along. L hat M left-hand side is equal to M bar L on the right-hand side. And when you get nothing, this is just an identity, it's exactly the same thing on both sides. This is very typical of lax pairs. You put it into the compatibility condition, and in some places you get identities, in other places you get the equation you want. So here we're looking at the 1-1 entry and we have an identity. I wanted to show you this for an important reason, which is that we have two different powers of the spectral parameter appearing. We have nu squared and nu to the power of 0. And what this means is we really have two identities coming from the 1-1 entry of this equation. Even though here it doesn't really matter. Later on this will be very important. Let's move to an off-diagonal entry now. Again, it's just basic matrix multiplication. Left-hand side, right-hand side. Oh, just off the page, but don't worry about it. Here, an important feature is that nu appears linearly in all terms in this expression. And what it means is I can just cancel out nu and everything stays together, rearrange it, and I get the LMKDV equation. So that's how this lax pair is associated with a nonlinear equation. A natural question to ask is what else can this particular lax pair be, what other nonlinear equations can I associate with this particular lax pair? By this particular lax pair, I mean I'm keeping the spectral dependence the same. So I keep linear in nu on the off-diagonal entries and constant in nu on the diagonal entries. Everywhere else, I take off the specific dependence on x that I had before, and I just put in some general functions of the lattice directions. And what I want to do is put these into the compatibility condition and see what comes out. So when I look at the 1-1 entry, I get two equations again like I did before because the spectral dependence is the same. So again, I'll have two different powers of nu coming from the 1-1 entry. But now instead of just identities, I have some equations on these arbitrary variables that I've introduced. 2-2 entry again, because the power of nu is just linear everywhere, I can cancel it out and I have one big expression coming from this entry. I have to look at the other entries of the compatibility condition as well, and I get a list of 6 equations, 4 of which are simple looking and 2 of which look a little bit more complicated. So what I want to do is solve this system in a general way, not making any arbitrary choices, up to a point where I can see the nonlinear equation or system that's associated with this set of equations. To do that, I have a rule. I have a tool that I can use. If I have an equality between any two different linear operators acting on different variables, then I can reparameterize this and write both a and b in terms of a new variable v. And I also get some, these kappas here are in the null space of the respective linear operator. They're like constants of integration, if you like. That's where the lambda and mu, the arbitrary functions that I showed you before, come from. So if you're interested in this, please look at it. If not, don't worry about it. What's important here is that I have some way to solve this system of equations up to a point where I get a nonlinear system. Let's have a closer look. So for this is the set of equations that I know can be associated with LMKDV, and I want to see what else they can be associated with, and I get this. Let's have a closer look here. I call it LMKDV2. It's also known as Hayes' first law. And in there, I have x and y, two dependent variables in this coupled system of partial difference equations. So before I just had x, now I have x and y. I also have some arbitrary functions like I had before. I call this LMKDV2 because if I set x equals to y in this equation, I get LMKDV back. All right, halftime. What have I done so far? Just want to give you an overview so we can go to the second half and everyone knows where we are. I've started with some lax pair with a particular dependence on the spectral parameter, but arbitrary functions everywhere else. I've put it into the compatibility condition, and the way this depends on the spectral parameter has dictated the set of equations I get from the compatibility condition. And I have a rule that lets me solve this set of equations up to a point where a nonlinear evolution equation becomes apparent. In the second half of this talk, I'm going to look at how I can let the lax pair depend on this spectral parameter, because it's this dependence that gives me the different kinds of sets of equations I can get, and that gives me the evolution equations. So this is where it all starts, and that's what I want to concentrate in the second half. Now, I said, the title of the talk is A Completeness Study on a Class of Lax Pairs. Here is the class of lax pairs that I look at. It's all 2 by 2 partial difference equation lax pairs with just one separable term in each entry of each matrix. And by separable, I mean they separate into a product of spectral terms and lattice terms. There are a lot of ways you can do it, but this is a very simple way to do it. Yeah, I'll talk more about the other ways at the end. So I have one term in each entry that's separable. I'll put that into the compatibility condition, and I get 4 equations, one coming from each entry of the compatibility condition. So I don't need the lax pair anymore. I'll just concentrate on these 4 equations for the rest of the talk. And I'm specifically looking at the spectral dependence now. To put it in the context of the example I gave before, these 4 spectral term products used to be equal to nu, and that meant that they all cancelled out of the first equation, and I just had one equation involving all 4 of the lattice term products that arose there. Same thing happened in the 2-1 entry, but in the diagonal entries, something else happened. The 2 spectral term products on the right were nu squared, but the spectral term product on the left was 1. And this meant that this whole equation split up into 2 equations here. Now, at this point, I want to remark that there have been other studies previously that did a similar thing, similar completeness studies on lax pairs, but always at the beginning of the study, they made an assumption about the type of dependence that the lax pairs had on the spectral parameter. For example, Ward in 1998 did a study on isomonodromy lax pairs, where he said that the spectral parameter can only enter into the lax pair in rational functions. If I want to find every single lax pair that can be written into this class of lax pairs, I can't make any assumptions about the form of the spectral parameter. But that's okay. If you see here, it doesn't matter. Same thing happened in that other entry. But if you see here, it doesn't matter that C xi and B gamma are nu squared. What matters is that C xi is proportional to B gamma, where proportionality is defined if f is proportional to g, then f is a constant times g. If they're proportional, then definitely these 2 terms on the right will be together, and I'll be able to cancel out the things that depend on the lattice variable from those 2 things. I need something else though. In order to split this entire entry up into 2 equations, I need to make sure that A lambda is not proportional to C xi and B gamma. If it was proportional, then the other terms would be together with this, and I have just one big equation there. Similarly, I don't need to have all of these spectral term products being nu. They can be anything so long as they're all proportional. That will allow all of the lattice term products to remain together in the compatibility condition, and it will give me the same set of equations that I had before, and I solved in a general way to get the LMKDV2 equation. So the question now becomes, how can I combine the lattice term products? And what equations do they give me? And then what nonlinear equations come out of those sets of equations? So if I look firstly just at the 1-2 entry of the compatibility condition, and I consider the spectral term products that arise there, I just look at how I can group these together. For the example I gave before, everything was proportional, and it led to everything being together in the set of equations. But it doesn't have to be like that. I can split them up into two pairs. Let's see this, how it's working. A xi is proportional to d xi. So I have this term proportional to this term, and the corresponding lattice terms come out in an equation. But split up separate from that, these are not proportional to these equations. They are proportional to one another. So this term and this term are together, and I get that in my set of equations. Very simple. But there are a lot of different ways how I can combine these spectral terms. Different pairs can arise, or I can have triplets and pairs. Heaps of different combinations of links, I call it, can come about in just this one off-diagonal entry. What happens? I don't want to go into the details in this short talk, but obviously there are so many combinations possible that you need to make other considerations in order to limit it to a manageable number of combinations, manageable number of lax pairs that you need to check. I will point out though, that for each choice in the 1-2 entry, those were all just choices in the 1-2 entry. Once you have a set of links in the 1-2 entry, you have to consider the other entries as well. Not all links in the other entries are compatible with the first choice you make. So you see which ones can go together, you make some choices for all 4 of them, and you get a set of equations. And once you get your set of equations, you use the rule that I described earlier and solve this for the resulting evolution equation. That's the method. These are the results. So of all of those combinations of links, what lax pairs did I find? Just 2. Only 2 were interesting in that they were nonlinear and they had exactly the right level of constraint in the system of equations. If you have too much constraint, then maybe you can reduce it to a non-interesting system, something that's linear or constant. Not necessarily, but maybe you can. If you have not enough constraint, then maybe the lax pair is false because you can write anything you want into the system with the freedom that's left open. But I did find 2 interesting ones. One was the LMKDV2 equation that I showed you before, and the other one, uniquely enough defined by the set of links, is the LSG2 equation, which is another coupled set of partial difference equations where if you set x equals to y, you get the lattice sign Gordon equation. So, future work. I'm the first to admit that this is a very limited class of lax pairs, as was brought up earlier. I did it this way because it's the easiest one to do. The completeness part of the completeness study is not really the important thing. It's just that the idea that you can do a completeness study by not choosing a fundamental function that the spectral parameter must depend on. So it's the fact that you can do it rather than the completeness study itself that's important. However, I would love to be able to do this thing with arbitrary numbers of terms in lax pairs that are not just 2 by 2 but are of arbitrary size. But I'm sure you can imagine the number of combinations of links increases very rapidly as you add more terms. So I need someone who knows how to work a computer to help me devise an algorithm so I can make these calculations automatically. That's it. Thank you very much.
Any questions?
You mentioned something very interesting, that not all the pairs you find are actual lax pairs. Something you get something that looks like a lax pair but is not.
Yes.
Could you elaborate? Is there any way you can tell whether what you find a pair of matrix is a genuine lax pair or not?
This is a very interesting question because, as you pointed out, sometimes something looks just like a lax pair and it's very, very difficult to tell that it's not. I found some lax pairs here that I can tell are false, but the only way is by solving the system of equations up to a point where there's freedom left over, but you have no more conditions. And with that freedom, you can write anything into the equations left over, and obviously they're false lax pairs because you can write non-integrable equations in there. So the only way I know, no shortcut, just working out the system of equations up to a point where there's freedom left over.
So Mike, somehow it would be advantageous if you can get rid of your gauge transformations to begin with, because lax pairs are up to a gauge transformation.
Yes.
If you could build that in, would that narrow your choices you have? Because combinatorics will kill you, if you do this in 3x3s and 4x4s later on.
Yes. The gauge transformations are definitely important. I have too many degrees of freedom in the system that I wrote, but they disappear naturally as you solve the system of equations. I left them in there so I can have nicer looking forms at the end, but you can take them out at the beginning. You still get the same number of combinations of links though, because there's enough freedom left over after the gauge transformations to still have the combinations of links.
The factorization you wrote is not invariant under gauge transformation. You start with a matrix which each entry is factorized, but
Yeah.
the ways the entries are factorized are completely different. So this is not invariant under gauge transformation.
I have to look more closely. I believe you, but
And
you
that's
can.
exactly what would help you, because if it is not invariant, then an arbitrary gauge transformation, which you can always apply, will actually narrow down the choices.
Yeah.
And therefore you will be able to weed out a lot of combinations.
Maybe, but I'm sure you can weed out a lot of combinations. I weeded out a lot of combinations by other considerations, which might end up being the same as what you're talking about. And I didn't talk about those in this talk. If you can weed out more using the gauge transformations, it's definitely helpful. So I have to look at it.
As a matter of fact, by gauging, depending on lambda, you can kill one entry in the matrix, spectral entry. By multiplying the whole matrix by another function of lambda, you kill another entry. So you have only two independent, of course, projective. Then one you can choose as a spectral parameter, because any function of spectral parameter can be chosen in your approach
Yes.
as a spectral parameter.
Yes. But still, it still leaves very many combinations. And the ones that I checked here, there were 15 basic classes that were left over after I weeded things out. And you can write them just the way you're saying, by having two entries as unity, one is a spectral parameter and one is a function of that spectral parameter. But the links still tell you, the links are still the important thing because they give you all the combinations, and each set of links was written in a way that you just described.
Any more questions or remarks? If not, let's thank the speaker again.